Hello, everyone. Welcome to day one of the 2021 summer series. Our first session is Gearbox plate designs with Code Orange, and our next session is electronics for FRC with the robot dolphins, and will begin at 5:50. So without further ado, take it away, Code Orange.
Hey everyone, welcome to Gearbox Plate Design. I'm Alan. A little background about me: I'm the Code Orange CAD lead this year, and I've just designed a couple mechanisms over the past few years on different Code Orange robots.
I'm Jonathan. I've been on the CAD team for I think 3 years now, and I'm just here for the demo portion of the workshop.
Oh yeah, so I think we'll get started now. So yeah, once again, this is Gearbox Plate Design, and just a quick note that Code Orange, we usually use SolidWorks for CAD, but if you guys have different CAD softwares, that's totally fine, because I think these basic principles on Gearbox design should carry over between softwares. So I guess we'll just start with the basics on just what is a gearbox. So if you guys read through this kind of block of text, specifically a gearbox is a contained gear train. So it's a box with gears inside of it that alter the torque and speed between the motor and the output shaft. So here's kind of a basic gearbox setup. We start off with the motor, and then we go to a pinion, which is kind of a smaller gear that's driven directly by the motor. And then from the pinion, we go to a gear, and then after that, we go to a shaft, and from the shaft, we can go to a mechanism. So that can be like an arm for like a climb, or like rollers for an intake. Here's kind of another diagram of a gearbox. So you can see we start off with the motor, and then we go into our input stage, or where the pinion comes from the motor and then drives a driven gear. So this is stage one, and then we can come to a second stage, or even like a third, fourth, or fifth stage. And then from that last stage, we go to our output shaft, which drives the mechanism. So here's where the importance of a gearbox plate comes in. A gearbox plate is essentially a guide or instruction manual for your gearbox. So essentially, if you have a well-designed gearbox plate, you have a well-designed gearbox as a whole, because the gearbox plate dictates the distances between bearing holes to make sure that your gears within your gearbox are properly spaced apart. So this is kind of Code Orange's process of coming up with a good layout sketch or a good gearbox plate. So we start off with goals and constraints. So these could be like torque goals. I need to reach a certain torque at the output shaft, or I need to reach a certain speed at the output shaft, and also like size constraints. Then from that, we go to a layout sketch. So this is just a basic sketch, not that basic, a pretty messy sketch, where I essentially sketch out and draw out where my bearing holes are going to be, where my motor is going to be, and where my mounting holes are going to be. And then from that, we turn it 3D. So the boss extrusion is when we take our layout sketch and turn it into a real plate. And then from that, we just go straight to assemble our gearbox, and then after, the last step is pocketing. So just a big emphasis that always pocket later, because a ton of times what I've done is I pocketed first because I get really enthusiastic around pocketing. But if I need to go back and change dimensions of my gearbox, it always gets messed up, because pocketing messes up, because I always just mess up my pocketing and I have to redo it. And just like an asterisk down here, every team probably has their own method, or have their own method of designing gearboxes, but this is just our way of doing it. If your team has a better method, that's cool as well. So just, yeah, quick note. And so we'll start off with, I'll walk through kind of this process. So we start off with our goals and constraints. So as for goals, these could be speed and torque requirements. So for example, an intake roller needs to be very fast, right? So we want to gear it for speed. So our gearbox would be geared for speed. And then a winch needs to pull the robot up. So we want to place more emphasis on torque when we're making our gearbox. And a few constraints could be like size constraints, strength constraints, or weight constraints. So like if our gearbox is in a very tight spot, located in a very tight spot, we might need to change the shape or size of our plate, or we might have to have a flipped gearbox just to keep the size down. And then there's also like strength constraints. So for example, if there's like a lot of torque that's acting on your plate, so like you're dealing with very high torque, you might need a thicker plate. Or like if your gearbox is outside exposed on your robot, and like it might be hit by like the wall or something, then you might want thicker plates. And then there's also weight constraints. So like if you're very close, we've been here a lot of times where we're like a quarter pound away from the max weight limit. You might have to do some more pocketing or gearbox, or like use the thinner plates. So yeah, those are just a couple goals and constraints to keep in mind when we're designing our gearbox plates. And then the next step would be a layout sketch. So here's just a quick diagram. We don't really have to pay attention to the rest of this stuff except for pitch circle and pitch diameter circle, pitch circle diameter. So what's really important when we're spacing gears apart within a gearbox is the pitch diameter. So essentially a basic rule with gearboxes is if we dimension two pitch diameters and make them tangent to each other in the middle, so they're let me turn on my. If we dimension two pitch diameters and make them tangent, so right here, they're tangent, only connected by one point, then the gears will mesh correctly. And here's just another example. So right now I'm going to be using a 48 tooth 20 DP gear and an 80 tooth 20 DP gear. So these are just two kinds of gears that we can get from Vex. And you can see these two sketch circles are pitch diameters. So this pitch diameter is 2.4 inches in diameter. This pitch diameter is 4 inches. So by making them tangent and spacing the bearings around this tangent relation, this allows me to properly space my gears apart. And on top of that, a quick side note is that sometimes, depending on like how accurate your machines are, or like your like whatever, if you're using like a router or a water jet to cut your plates, you might need to add a little bit of tolerance, because sometimes machines, they can oversize the dimensions or they can undersize the dimensions. So we want to be really accurate with the spacing between gears. So you might have to add like a tiny dimension to space them properly. So here's just kind of an outline of the gearbox layout sketch. So we first want to decide what gears we want to use based off of the ratio we want. So this comes from the goals and constraints that I mentioned earlier. And then on top of that, within our sketch, we need to include tangent pitch diameters, the motor footprint, motor mounts, and bearings. And so this a big emphasis on the motor footprint, because sometimes if the gears are too small, the motor, like the outer diameter of the motor, will interfere with some of the bearings within our driven gears. So this could be a problem, because then we can't fit a bearing anymore. So if we draw out the motor footprint, we can easily see if there are any problems with like the motor interfering with the bearing. So here's kind of example of a pretty simple gearbox layout sketch. So I'm just gonna go over point out all the big parts of it. So I'm gonna start with the motor shaft hole. So a lot of motors that we have these like hubs on the motor. So this is just a hole to fit the hub of the motor. So the motor can be attached to our plate. And the next is the motor footprint. So this can just be a construction line that just shows the outer diameter of the motor. And then we have our motor mount holes. So these are just like 2 or 4 holes, whatever, just to mount the motors. So this looks to be a Neo motor. So we're going to be using the 2 mounting holes that are on a Neo. And then next we have a bearing hole. So this is just a hole, a cutout, so we can put a bearing to support the shaft. And then right here you can see we have gear pitch diameters. So the first diameter is this big circle, and then the second diameter is this smaller circle. And a big thing is keeping our layout sketches organized. So a good layout sketch involves tons of overlapping lines, which is great, but it also becomes a problem because you don't really know what's going on after a while. So yeah, if I go back to this slide, this is a pretty simple looking gearbox. It's only a 1 stage. So I only have 1 pinion and then 1 driven gear. But if we're doing like 2 or even maybe 3 stage, if we're doing layout sketches for 2 or even 3 stage gearboxes, then we become a problem because there's just so many construction lines and like defined lines. So here are just a couple rules that we like to use. when we're making these layout sketches to make sure that there's like standards and like continuity between each layout sketch. So use construction lines to exclusively for pitch diameters and motor footprint circles. And then use normal lines or in SolidWorks, just like the thick defined lines, use these lines exclusively for motor mounting holes, bearing holes, and the outline of your plate. And then another point is sketch labels. So sketch labels are essentially allow you to just label different circles or dimensions within your sketch. And these are super helpful. These are sometimes super helpful when you're just dealing with a ton of different gears and different motors. So if you want, you can label pitch diameters with gear specifications. So like if I have a 2-inch pitch diameter, then I'll label that, oh, that's a 4220 DP gear. And then on top of that, motor footprint circles, you can label them as motor specifications. So I can point out, oh, this is a Neo motor, just for future reference if you're looking back at it. So here's kind of an example of a layout sketch. This is a this looks like this is a 2-stage layout sketch, and it's you can see the labels in action kind of. So you can see right here, I have an out motor footprint circle and type over here. It's a Neo, not a Neo 550, but here's just a good example, because when it gets complicated, it's really helpful to have labels. So that's kind of a basic rundown of how to create a good looking gearbox layout sketch and like a gearbox plate. So the next stage of this is going to be a demo run by Jonathan. So he's going to design a single stage gearbox with a 775 Pro with a 7-to-1 reduction. So yeah, Jonathan, take it away.
Yeah, okay. Let me pull up SolidWorks really quick.
Oh, and just letting you guys know, we will be answering questions after Jonathan's demo. So just like throw them in the chat or something, and then we'll answer them right after.
Yeah, okay. So Alan did a great presentation. We're just going to do a demo because it's a lot of information to take in. And usually I find it easier to learn by doing rather than just like watching a lecture. So we're just going to open SolidWorks. Remember, this is in SolidWorks and not another program. If you use another program, like Alan said, the ideas translate. So walking down the list of things to include in the layout sketch, I'm just going to start with the gears because that's pretty much the main part of the gearbox. And we will be using circles to represent the gears. And I already have the dimensions pulled up on another tab. And this will be the pinion, okay? And the pinion should be a construction line. And then I'll put a gear directly horizontal to the pinion. And these are both construction geometry because they're for reference. And the gear is 2 inches in diameter. And this will be a 7-to-1 gearbox. And it will be driven by a 775 Pro. So what I'm going to do first is actually the motor footprint. And the motor is actually 1.744 inches in diameter. And since this is also for reference, it's not a hole, I will be making a construction line. And then, like Alan said, there's a motor hub on every motor. And you need a hole for the shaft, obviously. And this is actually a hole in the plate. So it will stay a defined line. It's 0.689. And then I will just put in the mounting holes for the motor because we don't want to get the mounting, or we don't want gears to be in the way of the mounting holes. You guys can see that this big gear is actually kind of taking up some of the motor footprint. So we'll probably want to put the mounting holes vertically right here. I'm just going to use a midpoint line. And the bolt circle of a 775 Pro is 1.142. 1.142. Okay. And this is obviously for construction. And I'll just put holes on either side and make them equal by pressing and then shift and then click and then making them equal. Oops. Did I do that? Yeah, okay. And these are for M4 screws, and the clearance of M4 is 4.5 millimeters. All right, so our layout sketch is pretty much coming together, but there's one more thing missing. We've been through the pinion, we've done the gear, we've done the motor, pretty much everything concerning the motor. And then now we need the bearing hole for the big gear. And thunder hexes, those kind of bearings, those are all pretty much 1.125 in diameter. Yeah. And then since I guess we're pretty much done, we can just extrude this. Actually, not yet. You need to put a rectangle around it first. This is the simplest way to just turn your layout sketch into a plate. Obviously, if you're working with tighter dimensions, then you could extrude it differently, but this is how I would do it. I'm just going to dimension it 0.3 away from each gear. So up and down on the big gear, and then side to side on this big gear and this smaller. Actually, and the motor. So how you do this is you hold shift, click on the line, and click on the circle. That's how you dimension it. Now just go through these really quick. One more. Alright, so here's our plate. Pretty sure everything's on it. And I will be extruding it to 1/4 of an inch. I do that because when you put in a bearing in an 1/8 inch plate, it actually sticks out on the other side. That can become a problem when like the shaft can fall out. So 1/4 inch is usually nicest. And I don't think you guys want to watch me assembling the whole gearbox on stream. So I prepared the complete assembled version. So the motor goes here, right? The pinions go here, and the bearings are all on both sides. And you can reuse the same plate. So in this case, I use the same plate, but I also put standoff holes on all 4 corners. This is pretty much it. I also pocketed it, and if you guys want to see the design, or see what I did for the sketch. Sorry, that's not it. If you guys want to see the sketch, here it is. So when I pocket, usually I try to divide it in like four areas pretty much. And this time it was like an X shape right here, these 2 construction lines. Or it's pretty much like a center rectangle. And then it'll automatically make these kind of triangular shapes around the bearing. And of course, when you do this, you make a circle around the bearing hole because you don't want to make the bearing hole bigger. And then you're just basically removing material because it's too heavy. And that's pretty much it. I put some like rectangles on the top and the bottom of the motor. It wasn't necessary, but here's how it turned out. Do you have any questions, Alan?
Yeah, nice demos. Nice demo. So I guess now we open up to questions? Okay, I'm just gonna be reading through the chat on the live stream and just reading out questions. So how do you pocket effectively when manufacturing? Not really sure. So at least what we do when we manufacture our plates is we just do it on either like a CNC router or we're lucky enough to have a water jet. So that's kind of how we do it. We just someone just takes our CAD or Jonathan maybe takes our CAD and then he cams it. So he turns our like plate into a set of G code, send it over to CNC router or the water jet, and then just gets cut for us. If we were doing it just like kind of manually, I'm not really sure how we would pocket manually. But yeah, hope that kind of answers your question.
And pocketing is just removing material. So if you find like parts where you could just like drill big holes into, I guess that would work too.
Yeah. How do you determine the spacing between the plates? Jonathan, I think you can answer this question.
Yeah, so you usually want to keep the plates as close together as possible, because when you have a gear on a shaft pretty much, let me show you guys. When you have a gear on a shaft, there's like a force being applied on it pretty much. And the closer, or actually I'll say if it's far away from the plate or far away from a support kind of, if I put a gear all the way out here, then it would be able to kind of flex a little bit. So we want to put our plates as close together as possible. Obviously this assembly is pretty bad because I didn't put spacers in between the bearings and the gears. Usually you would put in like a tiny little spacer in there to reduce friction, but you want it as close as possible.
I'm muted. Do you typically use the same plate for both sides of a gearbox or not often? So at least sometimes we use the same plate, sometimes not. At least I'll say most of the time we have our like gearboxes, they're usually bolted directly to like a mechanism that has they're usually bolted directly to like a mechanism that has like an arm or something that has like the output shaft kind of built into the mechanism. So we usually only need us like one plate, usually only one plate. So like if we're like making a gearbox for like to spin like a hopper, then usually like we have our plate for the back of the gearbox that attaches the motor to the gearbox, but usually like the front is the hopper side plate or something like that. But it's really just up to whatever scenario it is, whatever scenario it applies to.
Yeah, I can say like if you're designing a 3-stage gearbox, you probably want to remove the motor mount on the third plate, right? But in this case, it was simplest just to copy the plate over. Of course, there's going to be scenarios where you want to make changes. But basically, the idea I want you guys to get is that if you have a layout sketch, then you can apply it to every stage, but just take out certain parts of it. If that makes sense.
Okay, so the next question is, how thin of webbing do you typically leave on each pocket segment / between them?
Wait, can you repeat that?
Hi, Mike. Here, Jonathan, do you want to read the questions?
Oh, wait, I don't have the link open.
Oh, sorry. I'll try and fix my mic while Jonathan.
No, I think your mic is open.
Oh, works?
Yeah, I can hear you.
Oh, okay. Okay, so how thin of webbing do you typically leave on each pocket slat segment or between them?
So like over here pretty much.
I was just thinking like the supports.
Oh, right here.
Yeah, like that. Yeah.
Okay. So this is like quarter-inch plate. So I left a quarter-inch right here. I'm not like really sure about the rules about the webbing, but since it's a pretty thick plate, I would feel safe with a quarter-inch. But make sure if you're dealing with high loads and stuff to, it doesn't hurt to put maybe a little extra unless the robot's overweight. And for eighth plate, maybe I would put like 0.3 or 0.4. That might be a mentor question, depending on like your team.
Yeah, it's really once again, this one's also really conditional based off of how much load you're thinking is gonna your how much load you think your plate's gonna experience. So yeah, for like a gearbox like this might be super high load, so like a quarter might work. But like for like something like a belly pan, which is like it's like kind of protected by your drive rails. What I like to do is I like to put around an eighth and like really, really thin pocketing because it really saves a lot of weight. But yeah, it's just really conditional. Um, how much room do you count for between the gear and the plates? Um, so at least for some gearboxes, oh, Jonathan, could you rotate your view to like a side view kind of like the gear and the bearings, or if you can do a cross section, that'd be
Oh,
great.
okay. This way?
Yeah. So
Okay.
if we look at
Well,
that this kind of look right here, at least in this scenario, we can actually just have no room between the plates and the gear because at least this is a Vex gear that we're using. The Vex gear has a built-in hub. So what that hub allows us to do is it allows us to put it right against the bearing because it's properly distanced away from the bearing so that the gear won't be rubbing against the bearing to introduce extra friction. And and yeah, it just distances the face of the gear away from like the the rest of the bearing. So we can pretty much just put the gear right against the bearing without
you
experiencing any
guys want to
friction.
know that kind of like hub on the gear is down here at the bottom right. It's 0.06 around there. Yeah. Oh, you're muted.
Oh, I was gonna read.
Okay.
So Jonathan, can you reopen the sketch?
Yeah.
I think someone wants to see just the dimensions that we have.
Sure. You guys can screenshot that. And if you want the pocketing one also, I can open it. I think my SolidWorks cuts off the numbers kind of or rounds up. So it might not be most accurate from this point of view.
Okay. I think we'll move to the next question. How do we choose gear ratios, and what is opinion for? So at least for choosing gear ratios, it's this one's also very dependent on what kind of mechanism the gearbox is for. So I'll just do an example for a drive base at least. So on just like a standard West Coast drive base, uh what we usually do, we've done a couple years in like 2018, I think. We had like the Vex Pro shifting gearbox. So that gave us like two gear ratios that can shift between. And one of them was high torque and one of them was geared for more speed. So I think this is a good example of how we choose gear ratios because it kind of gives us two states. So whenever we want to push a robot around, this is in 2018, whenever we want to like fight against defense or push a robot around, we would shift to the higher torque gear reduction. So this would be I don't know what the exact number was, but it would be like a 1 to 5. So from our driving gear to our driven gear, it would be a 1 to 5 reduction. That's just an example. I don't think it was that, but so that's like high torque. If you want to push something around, if we want to push something around, and then if we wanted to go fast, if we want to go fast and like do a lot of cycles really quickly, we would shift to the higher speed, quote unquote. So it wouldn't exactly be like a 5. So I'm talking driving gear like a 5 to 1. That would be way too fast. But it would be like a little bit. It would be like a little bit lower torque. So it would be like maybe like a 1 to 2. I'm not sure what the exact gear ratios were, but like it would kind of be like that. So it's just
Basically
dependent on if you want high torque or high speed. Sorry, go ahead.
Yeah, so like to calculate that, I guess if you want like speed, you get your end like what you want, and then actually wait, the motor speed, and then times whatever X ratio equals what you want, and then for torque that would be the same thing. You want or we use a JVN calculator also for torque, and that's like for the climbers and stuff and elevators.
And I think you can find the JVM calculator on Chief Delphi, or because I think that's where there's like a post there. So yeah, JVM calculator is really helpful.
Definitely.
If you were making something crazy like a 6-stage gearbox, would you need plate sandwiching each stage? Not necessarily. So pretty much the main idea behind having 2 plates for a gearbox is we're supporting the shaft at 2 points. So at all times within a gearbox, we want to support the shaft at 2 points, because if you only support at one, it's gonna start like doing some like it's gonna start trying to push the shaft up or push the shaft down, and it's gonna dislodge the bearing. So we always want 2 points of connection. So this can either be, can you go back to your old assembly, like the top level? Thank you. So it can be kind of like this, where the gear is sandwiched between 2 bearings, or it could be what we call like a cantilever. So we can have 2 bearings on one side and then the gear. Let me see if I don't have an example in my room, but like 2 bearings on one side and then the gear on the other. That also works, but we generally always want 2 bearings. So to answer your question, if you were making something crazy like a 6-stage gearbox, you could get away, I'd say, with having only 2 plates and then just having like a ton of bearings just like in a line going down or something. But sometimes you might want some like support in between, or like add like an encoder stage. Then you'd have to add a plate, but you can get away with doing only 2 plates.
Yeah, maybe something like this,
Yeah.
right?
So yeah, so
Or
that would be like a
cantilever.
cantilever. So it's kind of like levered over. I don't know why it's called a cantilever, but just kind of how it turns out. Next question. How do you typically decide on which direction the bearing flanges go?
Oh, okay. I think I can take this one. Um, Flanges basically stop the bearing from falling out in a certain direction. So you can see right now it's disconnected, and once it hits this flange right here, it'll stop. But you can pull it out this way pretty much. And usually a shaft has a snap ring groove over here. So a snap ring pretty much holds the end of the shaft. And when the shaft slides through, it'll hit the bearing. And since the bearing flange is stopped by the plate, then this whole shaft cannot move in this direction. And then if I put the bearing over here, the flange on the opposite side, and I put another snap ring groove here, then it will be stopped on the other side. But usually, I think it's kind of scary to put snap ring grooves in the middle of a shaft. So usually I'd find another way to retain the shaft. But pretty much bearings are meant for, or where the flange is based off of where you want to put snap ring grooves and where they don't get in the way.
And just to add to that, so if you want to like really kind of, so sometimes you have like a weird messed up gearbox where you can't necessarily fit like the two flanges on the outsides of the plates. When that happens, to determine like where to put your snap rings or like which direction to face your flanges, something that I like to do is I like to just take like a snip, use the snipping tool, and then just take like a kind of screenshot of the gearbox. And then from that, I'll just draw. So I just draw kind of where I just kind of think about it, oh, if I pull on this side, will the shaft fall out? Or if I pull on this side, will the shaft fall out? So I just kind of draw like little arrows, and then it just gives me a visual aid to kind of think about just like where the shaft can fall out, where the bearings can fall out. And then based off that, you can kind of helps you determine where to put snap rings, where to put bearings. And also on top of that, we like to use snap rings, at least for Code Orange. I know a lot of teams sometimes use like shaft collars or like bolts with a washer at the end of shafts. Those work too, but we just use snap rings because they're nice and convenient. Would you recommend the plates being square, or could you use irregular shapes like a trapezoid, or does it just depend on what you need it for? Yes. So most of the time it depends what you need it for. So like when Jonathan was catting this gearbox, he didn't really need to fit it around like some other geometry within the robot. So you can just do a square, which is pretty straightforward. But I will say though, having cool shapes like trapezoids or like a triangle or something makes the gearbox look way cooler. So yeah, if you want like the cool factor, the pocketing looks way cooler when you just do like a kind of irregular shape. But I would stress like quality and like capability over the coolness. But if you just have extra time or something, weird shapes look cooler.
Also, if like there's a mechanism here that was going to collide with the gearbox, you could totally cut this part off right here. And you can do like circles around each like gear and motor, and then do like a 1/4 inch around, or distance, sorry. Just depends like what's most convenient.
All right, so any more questions? Just if you have any more, just type them in the chat. How do we buy belts or chain? So where we usually buy them, at least for Code Orange, we buy them from Vex or actually West Coast Products. West Coast Products is very similar, sell a lot of the same things as Vex. It's just like the shipping's cheaper. So if you're on the West Coast Products, if not Vex or whatever close retailer sells the Vex stuff. But on top of that, for chain at least, if you want to do like different sizes of chain, I know Vex only sells 25 or 35 chain. McMaster is really helpful as well. They have like I think 35H chain, like heavy chain. They have some really cool chain sizes. So that works as well. And then where we also get belts is from a website called SDP/IO, stock drive parts or something. I don't know what it's called, SDP/IO. And they sell some really interesting. Oh, what? Oh, such I. Oh, whoops. They sell some really interesting like belts, pulley sizes. So like Vex only sells like a couple. This website sells pretty much everything from like 20 tooth belt all the way to like a 200, and then plus sizes like 720 teeth, 1,000 teeth. Really interesting. And they also sell thin belts, which are like 6 millimeter. And so I'm talking about, these are GT2 3 millimeter belts. So they usually come 9 millimeters thick. They also sell thin 6 millimeter belts. So yeah, and like cool pullets and stuff. That's a cool site that we also use sometimes.
Yeah, and I think WCP has a really good belt calculator for like measuring the distance you need or how big of a belt you need for a certain distance. So when you're designing, make sure you consult the calculator and make sure it fits those dimensions.
Yep. So it's about 5:40 now. Is that when I think that's when we're scheduled to end. Um, yeah, I hope you guys had fun. It was definitely a blast. Um, yeah, hope you guys learned a lot. Thank you for all the questions. Thank you for listening to our kind of a presentation.
Yeah, thanks guys.
Thank you everyone for watching. Up next, we have electronics for FRC with Team 5199, and that will begin in 9 minutes. Hey everyone, we are back with electronics for FRC with team 5199. Caden, take it away.
Hi everyone, so today I'm going to be going over just the basics of electricity along with all the components that you might see in a typical FRC robot. So starting off, probably the most basic thing in electronics, wires. Wires are strands of metal that carry the flow of electrons, meaning conduct electricity. We have two main types that we'll see: solid wires, visible in the top right. These you might only see if you do like electronics tinkering. Otherwise, on FRC robots, you'll always see stranded wires. These are thin filaments of copper all wrapped together. If you take multiple wires, or sometimes just one, and cover it in a shield of insulation, that's a cable. In the bottom right is a common cable, Ethernet. This is what you might see on the radio. So the basics of electricity. Voltage is measured in volts with a V. It's described as the electric potential difference or the electric pressure that pushes electrons through the circuit. More formally, it's called an electromotive force, a force that pushes electrons through the circuit, and it is basically like pressure in a pneumatic system. Resistance is measured in ohms, which has a Greek omega. It's described as the opposition to the flow of electric current, and it's largely based on like the surface area, volume, cross section of the wire, and the material. It's kind of like friction in a mechanical system. Current is amperes or amps with an A, and it's the number of charges, meaning electrons, that pass through a certain part of the wire in a given second. So basically the rate of flow over time. Power is measured in watts, and this is the rate of electrical energy over time. This can apply in a number of different ways, like the amount of power dissipated as heat through a circuit, or the power dissipated by a light bulb, anything like that. And then Ohm's law. So this is one of the most basic electrical engineering laws, but you'll see it come up over and over again if you keep looking at electronics. Voltage equals current times resistance. This is written V equals IR with I for current. And now on to some FRC components. So starting off, from our battery, we split the positive wire connection between the battery and the power distribution panel with our 120 amp breaker. So this component, it acts as an on-off switch for the robot, and it ensures that like a battery failure won't critically overload the robot and start a fire. So on-off switch, but if a current greater than 120 amps goes through it, it'll automatically turn itself off. Then our power distribution panel. Just a sec. Okay. Our power distribution panel takes power from the battery and distributes it out to all the robot's components. It also acts as the terminating point for the CAN bus, the main signaling system used on our robot. So it has lots of ports on the side to power things like motor controllers mostly, or other components. On each of those ports, it has breakers installed. These basically, when a current greater than the breaker's rated amperage flows through it, it'll pop and cut off the connection. Again, this is a safety mechanism. At the bottom, as you can see here, are special power ports for the PCM, VRM, and RoboRio. These are special components I'll touch on later. And in 2022, our next season, it'll be replaced by the power distribution hub, a new component. This has some cool new features like reading out your battery voltage directly, WAGO terminals, and a USB-C connection for debugging. So to go over some motor controllers, the Talon SRX motor controller is a brushed motor controller, meaning that it's used for DC motors like the 775 Pro. So this just directly takes in power from the PDP. is controlled by the CAN bus, and it regulates the amount of power flowing to our motor so that we can like finally control the speed. The SparkMax, so this is a motor controller with 3 wires coming out of it because it's used to control brushless motors like Neos, which are AC power. That's why we have a 3rd wire, and that 3rd wire is white. If you do use just the red and black though, you can still control a DC motor like a 775 Pro. The Victor SPX motor controller, this is much the same as the Talon SRX, but a little simpler, lacking features like current limiting, but usually functions exactly the same. So our pneumatics control module, PCM, this is also controlled by the CAN bus, and it's the hub for controlling all of our pneumatic components, our solenoids, which are electronically controlled valves, our compressor for actually generating that air pressure, and our pressure switch. The pressure switch limits our compressor to 120 psi as usual for safety. In 2022, this will be replaced by the Rev Pneumatics Hub. This again has features like USB-C for testing, better CAN terminals, and analog digital ports for our pressure switch, just for more variety. So our voltage regulator module. This is a small rectangle that takes in power from the PDP and puts it out as more finely regulated combinations of current and voltage. Most notably, this is what you will use to power the radio. And now onto the radio. So this is how we wirelessly control the robot. It enables wireless communication from the driver station and the RoboRio. It is powered by the PoE injector, which takes Ethernet from the RoboRio and power from the VRM. This, and to some extent the VRM, will both be replaced by the Rev Radio Power module in 2022. So this takes in a connection directly from the PDP and puts out a like well-controlled PoE connection directly to the radio. So the RoboRio, this is the robot's brain, as we call it. It's the central processing unit of the robot. It's controlled wirelessly from our driver station through the Ethernet from the radio. And this is what starts the CAN bus. It's the origin, because it sends out the signals to control all of the other components on the CAN bus. It also has PWM ports for controlling things like servos and digital input-output ports for things like limit switches. So the RSL is our robot signal light. It's controlled by a special RSL port on the RoboRio. It has a very specific way to be connected. If you notice, it has 3 terminals. So you need to take your positive wire that goes to LA, you bridge or jumper that wire to LB, and then your negative wire runs through the middle. So kind of a fork there. It has a couple different light up combinations which indicate certain things. So first, if the light's off, your robot's off. If the light is on and solid, then you're on, but in software, your robot is disabled. If it's blinking, then you're both on and enabled in software. To go more in depth on the PoE injector, this is power over Ethernet, and it's what helps our RoboRio and radio talk to each other. It just carries Ethernet and power in one connection, as the name kind of implies. And it's 12 volts at 2 amps from the VRM. The CAN bus. So the controller area network bus. This is just the main control signal that we use on the robot. It's used in automotives a lot, cars, and it starts at the RoboRio, ends at the PDP. It is daisy chained between motor controllers and the PCM, which is basically the connection flows into one motor controller and back out, into the next and back out. So just a big kind of loop that touches each component and then dips back out. So the signal of the CAN bus, it actually is sent because it's all one kind of joined wire, or really two. The signal reaches every component on the bus, but the signal is sent with a address, so it only targets a single component. So the RoboRio will point out a specific motor controller when it sends the instruction, so all the other motor controllers will ignore it. And on the topic of motors, these are basically, well, you wouldn't know, they convert electricity to rotation. We have a bunch of different motors available for FRC, so you have some things to consider when choosing one. You have to look at the torque of the motor, kind of its turning force, its RPM, which is how fast it rotates, and then the weight. Because motors are heavy, they can very quickly have you hit the weight limit if you have too many. Brushless motors, these are one of our two main types of motors. As I said earlier, they have AC power, so 3 wires go to the motor. This would be a Neo motor like in the bottom right. Brushed motors, these are kind of your more standard ones. They have just a red and a black wire. These are things like the Sim, which is a bit older, or the 775 Pro, which is still a good lightweight option. Brushless motors, to touch on some current models, the Neo and the Falcon 500. The Falcon 500 is a special case because only a red and black wire go to it, because it has a motor controller integrated on the back of it. So if you see how it's kind of 2 cylinders, that back cylinder is its motor controller. So motor controllers, these take power in from the PDP, and then the motor controller outputs that as a regulated power to the motor. Brushed motor controllers, I touched on them before, the Victor SPX and the Talon SRX, while brushless motor controllers are the SparkMax and the Talon FX. Again, that's our motor controller on the back of the Falcon 500. All right, so that's everything I was hoping to go over today. Do we have any questions?
We have a couple questions from the chat. So our first one is, does the amount of voltage affect how fast the current gets to the end of the circuit?
So if we go back to, there we go, Ohm's law. This is a kind of proportional constant relationship. So if we increase that voltage, then that current has to step up as a result, because that resistance is typically going to be fixed within our circuit. So you can kind of think of it as we have more flow, it pushes the electrons faster through the circuit, so we get more flow.
Okay, and then our next question is there a trick in order to plug wires into the PDP fast and efficiently without messing up the end of the wire?
So I would say that it's best to really twist it into a very kind of sturdy end cap that won't like come apart easily or fray. And then honestly, having 2 people there, one to use a screwdriver to lever open the terminal and one to just line it up, making sure there's no loose ends, probably the best method. But if I go to the PDP, now the power distribution hub, these use a new type of terminal, no longer wide mullers, which are the lever type. These are called WAGOs. So you basically flip open a latch, just put your wire in, and then close it down, and it'll actually kind of grab it and hook in. So it's a very secure and very easy connection.
Okay, thank you. And then our next question is, any tips for keeping the electrical components safe but still easily accessible on the robot?
I would say that the best way is to try and prioritize having them in an open area, or to have them be detachable from the robot. For example, if you have your electronics kind of down underneath your like your wheelbase, make it so that you can actually like slide out the panel on some kind of tracks, or just a couple screws and have the whole panel drop down. So try to just kind of, yeah, make it accessible and protect it with paneling, because polycarb panel is extremely light, still see-through, so you can see your issues, and very easy to just create a little bent box around it.
Perfect. And then our next question is, any tips for robust wiring, soldering versus crimped connectors?
It really depends. Crimping is probably a better choice most of the time, because solder can, yeah, for most FRC applications, I would say crimping is typically better, because you can always reinforce a crimp with solder. As an example, if you put a ring terminal onto a wire, you can crimp it. And if you still aren't like certain in the connection, you can then actually fill it in with solder to create a better bond between the wire and the terminal.
Okay. Another question from Teddy. Do any of the components require you to solder the wire to it, or would you only solder two wires together?
So I don't have a photo here, but the main component that you'll actually be soldering with is most likely the battery, because even though you can often find pre-built battery wires, this 120 amp breaker here, you kind of always have to cut your positive wire to put this in the middle, because those pre-built kits typically have the red and black wires the same length. So you can't just put it at the end without massively distending your wire. Those connections actually are, it's unlucky that the main wire that you typically have to solder is one of the hardest to solder, because this is a thick size 4 wire that you have to put ring terminals on. So my advice would to be using a soldering gun, just a high-powered soldering iron, basically, with a lot more wattage, that just heats up that really thick wire and thick terminal a lot faster. Because using a normal iron, you will really struggle to get the solder to melt down into the core of that thick wire. And also use flux just for the heat dissipation, because otherwise it'll again take 45 plus minutes for a single connection.
Okay, perfect. And then for the beginners, could you quickly explain what soldering and crimping and all that actually is?
Sure. So soldering, this is melting down a very low melting point metal, almost as a type of glue, a conductive glue. So you have a soldering iron in one hand, kind of like a pencil with a really hot tip. And in the other hand, you have a strand of solder coming off a spool. So you take your soldering iron, put it on your wire or your component, and then you feed solder in as it heats up, and it'll melt onto the component or the wire and hold it together. And then crimping. So crimping is basically just putting a terminal, which is some kind of like end piece, onto your wire. A ring terminal, which I mentioned before, this is a small metal tube that your wire sits in, and then a ring that you can put a screw in, or that you can mount on some kind of peg. There are some others like spade terminals. These are really secure terminals that bond together with another wire. And most common one that you'll see in FRC is Anderson's. Anderson power poles are a type of terminal that you have to crimp on. So these are latching terminals, because you put on a little metal tube, you crush it around the wire, forming a really strong bond, and then you put it into a housing for insulation so that you don't have that exposed metal. And then your connections can just click together very easily with right polarity every time.
Okay, and this kind of relates to the last question, but are there any good practices or tools for crimping?
For crimping, I would recommend investing in a dedicated Anderson power pull tri-crimp, I believe it's called. This just really helps facilitate crimping all the different sizes, because crimping can almost always be done using just a pair of pliers, maybe a screwdriver, to kind of, because your end goal is always to just crush the terminal around the wire. But using a dedicated tool can often make it a lot easier and have a lot less risk of your connections coming loose. And one wire coming apart can easily shut down your robot, so it's typically worth the investment.
Okay, perfect. And then what would you say the most important part of electronics is?
With electronics, it is, going back to what I just said, it is very important to have good practice and to just be careful, because it's such a interconnected system. Like if you cut off power to one component, it can lead to like shutdown of many other components or just failure of the robot as a whole. So just always checking your connections, making sure your cables are like held down with zip ties or tape or really anything so that they don't get caught on things. Making sure that when your team is like changing out a gearbox, that the wires aren't affected or pulled out somehow. Just small things like that, just to always be sure.
Perfect. And our next question is do you have any training advice and tips on cable management? So those are two separate questions.
For cable management, for training, here, I'll start with advice. So I would really recommend using zip tie mounts. These are small plastic rectangles with one side that's sticky, and on the other side, it has a crossway of holes. And these just make it very simple to kind of slap one on a tube on your robot and then run a zip tie through. Since it's a strong adhesive, there's not much of a worry because there typically won't be enough force on the wire to pull the mount off. And it saves a lot of trouble of having to like drill through a tube to run a wire through, which causes its own host of issues. Also, just this goes back to your electrical board layout, in that your cables will be managed kind of in main routes. So going back to my team's robot last year, we had a big passway of wires up from our turret, from the ball shooter, coming down to our power distribution panel. For cable management, we used a track to actually hold all of those wires together and secure them, rather than letting them all be kind of loose, free floating. So there's a lot of tools at your disposal to kind of just keep all your cables moving how you want and expect them to move. And let's see, for training. For training, I think the best way to learn cable management is really just hands-on, like making a layout and seeing what works and what doesn't is really helpful to learn and grow there. So this would be best on something like a practice bot or an off-season robot if you have the resources. Otherwise, just kind of taking components and laying them out and just trying things, I guess, to figure out how you can be efficient with your wiring and also careful with your wiring.
Okay, thank you. Our next question is from Taylor. Do you have a general breakdown of what gauge wire should be used when?
Okay. So this is actually something nice about this diagram here, in that the top right, you can see the thickness basically tells you what gauge. So most motor controllers are always going to be 12 gauge. This is kind of the standard that you'll be using for the most part anytime you're carrying a sufficient amount of power. For smaller components like the RoboRio, VRM, PCM, anywhere in the range of like 16 to 18, typically 18 though, will work. And this is just because they take less power in. Small things like sensors, the RSL, the radio, these can all get away with very small wires like 26 gauge. Sometimes you change it a little, but 26 is kind of the standard for those smaller, delicate, not very power hungry parts. And then of course the battery, you can again use a range, but don't go higher than gauge 6 because you'll add a lot of resistance that'll wear out your battery faster. And actually, I should have touched on this before. The higher the gauge, the smaller the diameter of the wire, and the smaller the cross section of the wire, the more resistance you have as you increase that power. So smaller wires are for like smaller parts, basically. It's pretty simple. And oftentimes you can estimate, but yeah, 6 for battery, 12 for motors and motor controllers, 18 for other parts, and 26 for like sensors.
Perfect, thank you. Our next question is from Sterling. What's your preferred motor controller for both brushless and brushed, and why?
I would say that for brushed motors, I would recommend in almost every instance using the Victor SPX over the Talon SRX, because though the Talon SRX has a lot of features the Victor doesn't, such as current limiting, for the most part, they just won't affect your normal usage. So it's more important to kind of save where you can, mostly money. And brushless motor controllers. The Neo 550s are really great because these are essentially a version of this Neo in the bottom right, except shrunken down significantly. So I highly recommend these if you need motors at the ends of arms or on intakes, anything where the weight becomes significant. And for those, I would recommend the Spark Max. However, for something like your drive base, the Falcon 500 is really excellent in terms of its just kind of all around motor capabilities, its torque, its RPM, everything. So that would be your best choice. And with its integrated Talon FX for any intensive duties.
Okay, thank you. Jonathan asks, is there anything that you would recommend to learn about electronics in our free time?
I think that outside of FRC, there is a lot to learn by just tinkering with microcontrollers. If you have an interest, you will find a wealth of information about the Arduino and Raspberry Pi. There are lots of other places to start, but those are great choices because they'll give you an introduction to electronics, a little bit of programming, and just expose you to a lot more than you'll see in FRC electronics.
And then Rue asks, any advice on having an electronics testing board for either teaching or prototyping?
An electronics testing board. So at least my vision of what that would be is mostly for your motors. So I would set up a board with one of each kind of standard motor controller or just a standard connection and have that as a way to easily check your motors that they're working. Otherwise, you don't exactly need a testing board. There is a tool in FRC and electronics in general called a multimeter. This is a very helpful tool because it has a thing called continuity testing, along with a bunch of other functions. Continuity testing basically lets you check if an electrical connection is kind of secure, that there's continuity in the connection from point A to point B. So that's a great way to test if power is getting to your components successfully.
Thank you. And then, do you typically have problems with the Neo 550s wrapping up wires as its outmost shell is the one spinning?
Ooh. I would have to look at it, but typically it's about how you kind of route the wires. And I can check really quick. I haven't worked with them in a while. The motors are slightly detached because they're on kind of a separate section from the base of the motor. If my memory serves me correct, I can check and get back to you though, if you would like.
No worries. Okay. Next one is, when would you use a brushed motor versus a brushless one?
So brushless motors, they, for most applications, have begun to win out. They offer just greater torque, less wear and tear on the motor over time, and more power efficiency, along with being able to be a lot smaller, such as that Neo 550. Brush motors, though, because they're kind of more basic, are cheaper. So it's kind of that trade-off of the new modern thing versus the slightly more traditional but less expensive option.
Thank you. And then the next one is, best recommendations for electronic tools for an FRC shop.
I would go with a multimeter, a crimping tool for Anderson power poles, wire cutters and wire strippers typically are found together. So wire strippers, these are used to take the insulation off of a wire so that you can put a terminal or solder it. Such as in the top right, those sheaths over the wires, we can take those off so that we can throw Anderson power poles on. Other than that, I would say a soldering iron, a little station. You typically find them together with like a solder tip cleaner and rolls of solder or spools of solder itself. And then I would recommend buying in bulk just a larger spool of wire. Don't go for like a smaller 10-foot length rather than just buy like a 50 or 100-foot, even if you're a larger team, and just cutting lengths off as needed. And that will cover most of your purposes for tools. Yeah.
Thank you. And then looks like I missed a question. Kylie asks, are there any specific safety practices that should be followed when doing electronics in FRC?
So there are. Basically, you never want to be working, whether it's soldering or crimping, anything like that on the robot if it's currently on. If you have ever worked in houses, you only want to touch the electronics when your breaker is off. Same thing with the robot. If the breaker is not off and the RSL is not off, you don't have your hands in the robot working on it. More specific practices are the battery that you want to be extremely careful with, because any kind of short from the positive to negative terminal can be very dangerous with just a large amount of electricity or a fire starting. So with that, yeah, just be exceptionally cautious with that and make your wires soldered for the battery before you attach them. So solder and create them to the correct lengths separately. Then you attach one, attach the other, and you'll be fine. Other safety tips: when you solder, having some kind of ventilation is very important, because hopefully you're using unleaded solder, but in general, the fumes are a bit hazardous. You don't want to be breathing them in. And so just even like a small desk fan rather than like a fume hood is totally acceptable. You just want to have some kind of ventilation.
Okay, and then we have two more questions.
All right.
The first one is, how often should teams replace batteries, and how should they be maintained?
I don't have a specific kind of guideline for how often to replace batteries. Rather, you'll begin to notice as you use the battery frequently, its voltage will begin to decay over time. So rather than a nominal voltage of, say, 14 volts, well, really 12, but it'll hit a voltage of around 14 volts. It might creep down over time to like 13, 12 and a half. And that's like your big indicator that it's beginning to be worn out. So just as these batteries get used more and more, their voltage and their capacity will both fall. Really, it's more up to you of what limits are acceptable, because obviously a battery with less capacity and that can power your robot less isn't what you want, but you definitely can use it. On our team, batteries, when they're fresh, are competition batteries. As they begin to be worn out, they're practice only. And finally, if they're really just not working, we'll dispose of them.
Okay, perfect. And then our last question is, what kind of power pole connectors do you use? And then do you use Andersons?
Yeah, so we use Anderson power poles. These you can find, or I typically buy them in bulk from powerworks.com. These, they have a few different types: 15, 30, and 45 amp rated connectors. 15 amp are the smallest. These are if you want to put a power pole on a small wire like a sensor. Let me go back to the diagram. So yeah, any of these smaller wires, if you need to splice or jumper them, putting on a 15 amp connector would work. Slightly thicker wires can use 30 amp, and then your motors and motor controllers, these will be 45 amp Anderson power poles. What's nice about power poles is that even though you have 3 different sizes of these terminals, the outer housing, the plastic part, all works in between them. So you can connect a 15 amp power pole to a 30 amp power pole. You typically wouldn't, but it definitely won't like not work. And yeah, that should be it on Andersons.
Okay, thank you. And then before we go, do you have any last words of advice, anything we didn't cover today?
So FRC Electronics is a phenomenal way to learn the skills. I highly recommend, though, learning on your free time about what interests you, because FRC Electronics is great, but there are a whole host of other things in electronics that you've never even seen. Wireless communications, how batteries kind of work at a basic level, all kinds of different topics. Just explore, see what interests you. And thank you. This was great.
Thank you, Caden, and thank you everyone for joining us today. That concludes the first day of the summer series. Tomorrow, Team Spatter will be presenting on drive bases at 5 p.m. and then at 5:50 we will be having a training a CAD team panel. Thank you all.